the next concept is called the butterfly effect, or otherwise known as the chaos theory. Now, there's actually a very interesting story behind this theory. Edward Lorenz was a meteorologist in the 1960s. Edward Lorenz wanted to predict the future, and as an intelligent mathematician, he quickly learned that he could not do that. During the peak of his weather forecasting career, Lorenz utilized a computer program to simulate weather patterns by inputting various atmospheric coordinates. His objective was to gain insight into the conditions humanity would encounter in the coming month, which seemed like a straightforward task. And as expected, Lorenz obtained certain predictions from the initial run of the program. But then, like all good scientists, he decided to run the program a second time, just in case. While that happened, Lorenz went to pour himself a cup of coffee in the lobby of his lab, and when he returned, he was astonished. Despite utilizing the same atmospheric input, every prediction from the second run was entirely different. Lorenz said that the numbers coming out of the printer had nothing to do with the previous ones. And after some playing around, his surprise got even bigger. Turned out that the computer had rounded his input slightly differently during the second run. And when we say slightly differently, we mean infinitesimally slight adjustments. Surprisingly, these very small changes had a profound impact, altering the future in a significant manner. Eventually, Lorenz came up with a name for his weather mishap that seemed to place randomness over a table of underlying order. This name is the butterfly effect. So it seemed like that the flapping of a butterfly's wings in one location can potentially set off a chain of events that eventually leads to a tornado or a hurricane in another location on the other side of the world. So this is why this concept is called the butterfly effect, and it is used to explain chaos or non-linearity in systems. So this concept illustrates how a small disturbance can have a magnified and non-proportional effect on the system as a whole. And as we already saw, one obvious example of a system where non-linearity is evident is the weather system. So weather exhibits complex and non-linear dynamics, and small changes in initial conditions or input parameters can lead to significant differences in the resulting weather patterns. So the Lorentz system is used now widely as a simplified model to illustrate chaotic behavior. Now, the equations for the Lorentz systems are these equations. In these equations, x, y, and z represent variables that describe the state of the system, and sigma, rho, beta are parameters that control the behavior of the system. So these are the equations that are turned into a simulation model, and we are going to see how this simulation model functions in order to visually check out the butterfly effect. So this is our model, and in this case we are going to control only one of the parameters, which is rho, and we will be able to see that even when controlling only one of the three parameters, we will also be able to see different effects for each file. So let's just run the model to see at first how the results will be when using rho equal 28. Now let's see what will happen if we use a slightly different rho of 27. So we can already see that the path that is being created is already different than the previous one. So the trajectories that is being followed is completely different. It started from a different point, and it's going in a different order to draw or to end up with a shape at the end. And of course, as we change rho further from its initial value of 28, the more difference we will observe in the trajectory and the ending figure. Let's try with rho, let's say 10. So now we see a completely different shape. In addition to the different trajectories followed and the different paths, we also see at the end a different shape. Now let's try with a higher row of 35. And again, new paths, new trajectories. Although the final shape might be similar, it is similar to the butterfly, and this is another reason for calling the effect the butterfly effect. But still, the trajectories that are followed, the way the lines are moving is totally different, and the dimensions or the size of the final figure is also different. So this proves the idea that any small difference or disturbance in the initial conditions will lead to completely different results in the resulting system at the higher level.